So hi guys, today I wanted to show you about the amplification an operational amplifier, or short OpAmp, can do for us. And so we have here in the middle an operational amplifier drawn as a rectangle. So to the right side here is the plus input terminal, here is the minus input terminal of the OpAmp. And now we put some voltage in. And then the question is, okay, what voltage is at the output? So let's start. So this point here is connected to ground. And let's say we put, what do we put in? I'll say, well, let's put plus 1 volt in. Let's do that in a nice shiny color, green. So plus 1 volt in. And now plus 1 volt is here. So here, 1 volt. And yeah, now the question is, what is at the output? And as you know, sometimes the general rule, an operational amplifier, OpAmp, always wants to get the two input terminals to be the same value. Yeah? And it's only then, when the OpAmp has managed to do so, that then there is no delta between the input terminals. And then if these two are equal, then the OpAmp will stop operating and doing stuff. It would just simply do nothing anymore when the input terminals are equal. So let's assume this OpAmp, this OpAmp makes it. So we have two different explanation ways. So first, let's assume the OpAmp manages and it gets this to be 1 volt here. This input terminal, this negative terminal. Then we would ask ourselves, okay, we have two resistors here, and here we have the output. The output is connected via this resistor to 1 volt, and then via 1 volt through this resistor to ground. And let's just imagine for the moment both R1 and R2 would be, let's say, 1 kilo ohm. So R1, let's assume it to be 1K for the moment, and R2 to be 1K, just to be easier for explanation. And then what would that mean? That would mean you have 1 volt dropping down to ground over this resistor to the 1K. So there must be 1 milliamp flowing through this resistor here. Let's draw it in this way, 1 milliamp. And because there is no current flowing into an input terminal of the OpAmp, that's the second golden rule of the OpAmp. When here is flowing 1 milliamp, yeah, where does the current come from? Yeah, it doesn't come into or out of the OpAmp, so it must come from here above here, the 1 milliamp also. So there must also be 1 milliamp across here, 1 milliamp across here. And what does it mean? 1 milliamp flowing through a 1K resistor. Yeah, there must be 1 volt voltage drop across the resistor, because the voltage U through the resistor is its resistance times its current through it. And that we have for R we have 1K, and for I we have 1 milliamp. 1K times 1 milliamp resistor is 1 volt. And so we see it's really so this has to be, on this side we have to be 1 volt higher than on this side to make 1 milliamp flowing through it. So we are here at 1 volt to the left. We must be 1 volt higher, so here we must have 2 volts. And now riddle solved, because if we know this line here is at 2 volt, hey, that's the output. That's the output line where we have 2 volt. So this must be 2 volts. Yeah, and that's about it. That's our input-output behavior. We put 1 volt in, and we put 2 volt out. And then you can do another thing. We can move to that resistor here, R2. Let's say we have another case, and we draw it in red. And the case is that this is a 2K resistor here. Again, same situation. We put 1 volt in. 1 volt is here at the plus terminal. Then the OpAmp tries to get that also to 1 volt to the negative terminal. It does it from itself. That's its job, so to say, to get the terminals to the same potential. And now if we have again 1 volt here, and this is still a 1K resistor, then still there's 1 milliamp flowing through here. Again, the 1 milliamp doesn't come out of the op-amp, nothing goes out or in the op-amp from the input terminals. So again, the 1 milliamp must come from above here. And now this 1 milliamp that flows through here, it flows through a 2K resistor, not a 1K resistor anymore. And again, voltage equals resistance times current. But now the resistance is 2 kilo ohms, but the current is still 1 milliamp. And so we have a 2 voltage drop over this resistor. So being here 2 volt higher to be able to flow from 2 volt here to lower voltage, 2 volt low voltage to left of the resistor, the 1 milliamp. And then, okay, we have 1 volt here, we must be 2 volt higher here to the right. So that is 3 volts we have at the right side. 3 volts minus this 1 volts means a 2 volt drop over this resistor, 2 volt leading to 1 milliampere over a 2K resistor. So now, in the red situation, we put again here 1 volt in, and we get here now 3 volts at the output side. Okay, so the rule is in general, it is the voltage at the output, V out, equals 1 plus R2 divided by R1, R2 divided by R1 times the input voltage. And let us, for the green case, let us verify. Okay, the output voltage we want to have. So as input voltage, we put in 1 volt. Okay, here 1 volt. 1 volt. What is in the parentheses? So in the green case, V out equals, what do we have in the bracket? So 1 stays the same plus, okay. What is R2 over R1? In this case, it is 1K in the green case. So this was the green's initial case. We can also do that green. So 1K over 1K. And so, okay, 1 over 1, that is just 1. 1 plus 1, then, oh, that's 2. 2 times 1 volt. Oh, that drops out 2 volts. Oh, and that's exactly what we have seen. Okay, the formula predicts what we have seen correctly. Okay, and then the red case, let's start again. Okay, we want to know V out equals. Okay, so that parenthesis stays the same. Again, we put in 1 volt. And what's in the parenthesis? Okay, 1 plus, it doesn't change. But now we have 2K for R2. So we have 2K up here divided by, okay, R1 stays the same. It's in the red case also 1K. So 2K over 1K. Okay, let's see, what is this? 2 over 1K, 2K over 1K. Okay, that's simply 2. 2 plus here in front 1, that's 3. 3 times 1 volt. 3 times 1 volt, that's 3 volts. Hey, okay, 3 volts, 2 volts. The formula predicts quite nicely what we have rationalized on the graph. And that's it for this one. Thank you for watching. Please like and subscribe if you found this interesting, and we'll see you the next time. Thank you.